you can see the screen, right?
Yeah.
Okay. Um, awesome. So this is the last few topics of chapter 6, and I think you've sort of covered satellite motion, but I thought I'll refresh you a little bit. So satellites, we are putting up more and more satellites um, up in space for all kinds of reasons, for communication, for satellite, for weather communication, news communication, etc. And each country wants their own satellite, so it's getting pretty crowded up there. So um, you should know the basics of satellites. And so if you look at the diagram on the screen here, you'll see that the difference between a projectile and a satellite. So if you start off launching something from the Earth's surface, you know that if you throw it by hand, for example, it's just going to land up somewhere on the Earth's surface. It'll follow a parabolic path and land up again on the Earth's surface. However, if you throw it faster and faster, it'll go through big distances before it falls back. And it was figured that there should be a velocity with which one can launch a object or a satellite as it's called, such that instead of coming back on the earth, it'll just orbit the earth. And indeed that is definitely true. And that's how a satellite is launched. We start from the earth's surface and we give it a sufficient velocity such that the velocity is enough to follow a circular path. And so we're going to see the basic forces that act on the satellite once it's reached an orbit at a distance r, for example. Um, so the two, let's see. Okay, um, so obviously, if there were no gravity, if anything is launched, it's going to go off in a straight line. But because of gravity, it's going to kind of fall around the Earth's orbit, and so we are going to. So these are. So this is what helps us determine the equations of the satellite. So you'll see that for it to move in a circular path, um, there are two equations that a satellite is subject to. So if you look at the satellite that is on the screen, and let's say it's at a distance r from the center of the Earth. All distances are measured from the center, not from the surface. So um, so if you think of the satellite that's orbiting, you can see it on the screen. Um, so there are just two forces that act on the satellite as it orbits the Earth. Um, and it's a very simple equation because the Earth's gravity force, which is gmme over r squared, right? That's Newton's law of gravitation. And the the little m there is the mass of the satellite. So that would be the force of gravity according to Newton's universal law. And that should equal the centripetal force because there's nothing else that provides the centripetal force. Um, so the two have to be equal. It's similar to sort of taking a stone and tying it at the end of a rope and, sort of um, throwing it around. So the stone in that case, the centripetal force is provided by the tension in the rope. And you would put the tension is equal to mv squared over r. But in this case, there is no tension. So the only force that's keeping it moving in a circular path is the force of gravity. So those two have to be put equal. The little m is the mass of the satellite. And you can see that the m cancels off, right? And that equation should give you the velocity of the satellite. You see that the v there is the velocity of the satellite. So it's an extremely simple equation. It combines Newton's law of gravitation with Newton's F equal to ma, and together you get you can get the value of V. And although it's such a simple equation, this is exactly what NASA uses to launch satellites. They have to know what's the relation between velocity and the distance above the Earth that they plan on having the satellite. So yeah, in all cases, this holds good, and it's a pretty accurate relation. So just yeah, so I've just written it up in a way that's more clear. So you can see M. No, so M could be the mass of, it's a general argument, but let's say M is the mass of the satellite and ME is the mass of the Earth, right? The Earth, of course, is represented by the bigger circle, the blue circle, and we always measure distances from the center of the Earth, not from the surface. So the force of gravity, of course, is shown by an arrow going inward because it's, the force an attractive force. And so it goes away from the object. And so we put together mv squared over r equal to gm em over r squared, the way we saw before, and that gives you the velocity. And the other important factor is the period of the satellite. And of course, the period is just like we saw for the, I probably didn't do that lab with you, but the period in general is the time taken for one complete oscillation. So in this case, what would be the time taken to complete one, rotation or one revolution? It'll be 2 pi r. So what would be the time taken by the satellite to complete one full circular path? I mean, that's pretty simple concept because it's going around a circular path. So one circle would be 2 pi r. So the time period would be 2 pi r divided by the orbital velocity. So if I take the orbital velocity from the top and plug it in down in t, you'll get that expression for t. It's not really necessary to remember that, or just remember that t is distance by velocity, right? The time is distance by velocity, and the distance here is 2 pi r, and the velocity is v. So that you should be able to solve for the period if you just knew the radius of the orbit. That's all you need, because once you have the radius of the orbit about at which it's supposed to be launched, then you can find out the orbital velocity and therefore the period of the satellite. So yeah. So here I've summarized the two important equations. One is for the velocity of the satellite motion, and the second is for the period. And you will always be given g, the universal constant of gravitation. And remember that you can also put it on your formula sheet or whatever. I know things have changed a little with this online stuff, but yeah, I mean, I would definitely allow that, or I would have put it up on the whiteboard or blackboard for if you were actually doing a test. But those are things you don't have to memorize necessarily. The mass of the Earth also should be given to you. And R, now R is the distance above the Earth's surface. So, or I'm sorry, above the center of the Earth. So you should probably know how to get the Earth's radius, and that should also be given. And so I'm going to take an example to show how these things work in an actual problem. And okay, so I don't know if you can see, it's a little squished up because I tried to get the entire problem on one screen, but so here's a typical problem. So a 15 kilogram satellite orbits the Earth at an altitude of 2.5 10 to the 6 meters, which is a pretty you know, standard distance that one seeks to have a satellite in. So what's the orbital speed and what's the period? So it's pretty straightforward. The thing to note is that the R that you use for the orbit uh, distance should actually be the radius of the Earth plus the altitude. So that's one common mistake, because the R is not the distance from above the surface, it's the distance from the center. So you'd add the 6, so the radius of the Earth is around 6.38 times 10 to the 6. And so to that, we are going to add the altitude, which is 2.5 times 10 to the 6, giving you a total of 8.8 or so times 10 to the 6 meters. And then you have just put together the force of gravity Ft, just to make it clear that that's how you go about doing this problem. And then rather than, just use the formula, because sometimes maybe a different version is asked, so it's good to know. So then eventually you solve for V, and that's what you get. Okay, and then the period is the time taken to complete one rotation, and so you have 2 pi r over V. So this is how an actual problem would appear. And you can see that I think you've noticed that the mass of the satellite does not appear anywhere. And so that could be just to throw people off, that they're trying to fit in the mass of the satellite. It cancels out, because you can see from the basic equation of the satellite that if you have gmm over r squared is mv squared over r, the m cancels. So it does not matter whether it's a 1 ton satellite meant for something else, or a tiny little satellite for to report the weather. It does not matter. The mass simply cancels out, and so it's very convenient. We just have one value of the velocity that's required for a given distance from the center of the Earth. It does not depend on the mass of the satellite. And okay, so the next category of problems, you might have seen many of these in the homework problems, if you've tried any, is the relation between little g and big G. I think that we went through that in PowerPoint number 1. I'm not very sure, but I posted that and you can check on that. I think we did a bunch of slides on that, but I'm not going to repeat that formula, but it's simply given by little g equal to capital G m of the planet divided by r Earth or planet or whatever squared. So, so the problem is worded in a somewhat different way. When an object is dropped with no initial velocity above the surface of some planet big alpha and falls 13.5 meters in 3 seconds, and the radius of this planet is given, what's the acceleration of the falling object? So, so this is a problem where you'll find that if you're just looking to apply the equations of chapter 6, it may not be enough. And you have to go into the kinematical equations that you did in chapter 2, because the fact is those equations of Newton actually come about in just about every chapter. You'll keep seeing them. So because they are so versatile, you can use them for all kinds of situations. And so you have to search for the appropriate equation that you would use that relates. So I think you've learned the basic technique for solving problems, which is that you make a list of quantities that you know and make a list of what's desired. What do you need to find? And then try to relate what you need to find with all that you know. I think that's a logical approach. And then find out something that works, that gives you what you need to know in terms of whatever is given, and then take it from there. So let's see how this could be done in this case. Okay, so you can use, for example, the d equal to half at squared. You could, or you've seen it as y equal to y0 plus v0 yt plus half at squared, right, as part of your kinematic equations of chapter 2. And going back to the actual problem, you're given the distance, it falls 13.5 meters in 3 seconds. So that would be an appropriate equation to use. Y equal to y0. Now you may say, oh, I don't know y0 and etc. That it just means the displacement y minus y0. You can just take y to be 0 or whatever. For example, you can choose the ground to be the 0, just below the launch point. Then the final y is 13.5 and the y0 is 0. And then you know t, and you know v0 because it's dropped. And when they say it's dropped, it means initial velocity is 0. So all those things may not be spelled out, but by now, hopefully you have seen enough of those problems to see how it, this can be done. So yeah, so eventually the equation will be y or d equal to half at squared. And the catch here is do not automatically put a as 9.8 because we are not on the surface of the earth. So you have to, in fact, you're solving for a, which is why I chose a and not g. We normally call the 9.8 as g. So whatever planet that is, we have to find the acceleration, and that would be 2d over t squared. And it turns out it's very small. It's 2.94 meter per second squared. And so let's go to the B part of the problem. So the first part you know how to do now. What's the acceleration? What's the mass of the planet? Big alpha. So to get the mass, again, you should use what we've been using before, that if you had an object on the surface of the earth, by surface, I mean just, a few meters or centimeters away is pretty much the surface of the earth. So the weight of the object is m times g, or in this case, m times a. So let m0 be the mass of that object. So its weight is m0a, and the pull of gravity is gm mb, where b is the mass of big alpha. So you're trying to equate Newton's universal gravity force between the object and big alpha. You're trying to put that equal to the weight of the object on big alpha. So you get that equation that's, in the B part, the main equation. And then, so you simplify and you get mass of big alpha is AR squared over G. Now remember that the G here is truly a universal constant. It does not change whether you're on Earth or big alpha or little alpha or whatever you're on. It's only the little g, the acceleration due to gravity, that changes a lot. And we know how it's related to capital G, and all these problems sort of are based on that. So in any case, that solves or you solve for MB to be 1.52 times 10 to the 24 kilograms. So hopefully that's pretty clear. And we're going on to one last problem, which sort of summarizes this whole concept. So you have an object that's dropped with no initial velocity near the surface of some planet. And this time you're given the speed it reaches. So in 3 seconds after it's dropped, it's seen to be moving at 21 meters per second. And if that planet has a mass of 2.3 times 10 to the 23 kilogram, what would be the g on that object? What would be the acceleration of gravity on that object? And what's the radius of that planet, right? So I hope you see that it's a similar problem to the previous one, but you have to search your inventory of kinematical equations to see which would be appropriate. So in the previous case, you were given a distance, so you could think of d equal to half at squared, or y equal to y0 plus v0y plus half at squared. And but here you're given the velocity, so you should think of the equation. One equation that should come to mind is v equal to v0 plus at, right? You see that? And so v0 because it's dropped, it's no initial velocity, and the final v, so you can use that to get the acceleration due to gravity. So let's take a look at that. Okay, so if you put the v equal to v0 plus at, if you substitute everything that's known, you can solve for a, the acceleration due to gravity on that planet, and it turns out to be 7. So yeah. And then the you can let's see, what's the b part is to what's the radius of the planet. Okay, so to get the radius of the planet, you again use the usual relation, that is the weight of the object should be equal to the force of gravity of the planet on the object, right? And therefore you have that equation that you see, the usual equation. And if you simplify it, you get r. Okay, so I'm hoping that these problems sort of illustrated exactly how you would deal with satellites in orbit, find the velocities and periods, and how you would find the relation between g and or how you would use the relation between little g and capital G to solve all kinds of problems regarding planets and on the solar system, or any kinds of planets. We can get information from them from these kinds of problems. So I hope that's pretty clear. I think I'll so if there's a question, if anyone has a question, you can ask. And okay, so if not, I'll just continue, and then we'll have a question and answer session at the end. So, okay, I know there's one of the homework problems where there's an elevator problem, and that's fairly common. And the whole concept of satellites is also connected with, why do astronauts feel weightless in orbit and so on. So, okay, so objects in a satellite experience this effective weightlessness. And what it means is that it's exactly what you experience when you jump up and you're free falling. Apparently it's we have to talk about what free fall is and why there's no normal force. And so this is best understood by taking the example of an elevator, because actually you have to apply Newton's second law and draw an FBD of all the forces acting on the object. And that should make this a lot easier. So let's look at that a little carefully. Okay, so the first case we're going to look is, so you can see an elevator here, and let's say there's a mass m that's attached to the scale. And so if the elevator is at rest, means it's not moving at all, then we know that the weight of, so if you do an FBD of the object that's hanging, the two forces on it are the mg, right, and the upward force. Okay, so I guess the W there is confusing because normally we write W as going downward. I just put it as the tension in the string or whatever, but I guess it's called W because it's registering the weight of the object on the scale. So as long as it does not lead to confusion, you can call it whatever you want. But if you do the FBD of the object, there's the W going up and the mg going down. And if the acceleration of the elevator is 0, that means there's no net movement, then W has to be equal to mg by Newton's second law, right? Summation of Fx or Fy in this case, summation of all the forces has to be equal to 0. And so you have W has to be equal to mg. So it'll read the correct weight. It'll just read the mg. You see that? Because it's exactly balanced. The W has to be equal to mg. However, things change when the elevator is starting to move upward or downward. And then that's when the reading on that scale is going to change. And we are going to see why that is so by, again, analyzing by drawing an FBD and looking at Newton's second law. So let's go to the second case where, so in this case, the elevator is moving upward. And so again, you're going to apply Newton's second law. You have the same two forces as the FBD shows, the mg going downward and the W going upward. However, if I now do the Newton's second law and put the summation of the two forces, you can see from the top equation that summation F equal to ma actually gives me W minus mg equal to ma. You see that there are two forces acting on this object, and so you'll have that the net force, if I take the upward direction as positive, you're going to have W minus mg equal to ma. You see that the net force, which is one is in the upward direction, one is in the downward direction. So the net force is W minus mg equal to ma. And so the scale will actually register a weight of W equal to ma plus mg. It's not mg anymore. So the weight of that object is no longer mg, it's actually mg plus ma. So I hope you see that difference, because it's no longer at rest. If it's at rest on the earth and nothing's moving, then the weight is mg. But if not, it is not going to be mg. It's going to depend on let's say the earth itself is accelerating, then that would make a difference. So in this case, since the elevator itself is accelerating, there's going to make a difference. So the apparent weight is actually mg plus ma, which is greater than mg. So the person experiences or the scale reading is actually going to be more if the elevator is accelerating upward. And I think you can guess what's going to happen if the elevator is moving downward. Oh, just 1 second. Yeah, sorry about that. So you have so in the last case, we have this case where the elevator is accelerating downward, not upward. Okay, in that case, what happens? So if you draw the FBD again, you're going to have that W going upward minus mg going downward should be equal to ma, but the a itself is negative. You see that because the elevator is accelerating downward, so you have to put the minus a because acceleration is a vector, and you have, if something else is positive, that is in the opposite direction, then acceleration has to be denoted by a negative value, right? It is a vector. It's not a it's not just a number. And so if you solve for W, you're going to get W equal to mg minus ma, which is less than mg, right? And so you're going to find that the scale reading is actually less than mg. So the weight is a relative thing, right? Obviously, it seems to depend on the state of motion in this case of the elevator. And so what's the only constant here? It's the mass that's a constant, not the weight. Weight depends on g. So which means that if you take, even if you don't have any elevator accelerating up and down, if you took the same mass and took it to the moon, it's obviously going to weigh 1/6 of its weight on Earth, because the acceleration due to gravity on the moon is 1/6 of 9.8. So, so the weight itself is dependent on the state of motion of the object, whether it's being accelerated or not, and also it's depends on the acceleration due to gravity. So okay, so in the last case we're going to see is, okay, so in this case what happens, so we're talking of free fall here. What happens if the cable breaks, the elevator cable breaks, and everything's free falling? So in that case there is no there's just, you know, gravity acting. There's nothing upward to support it, and so it's going to register no weight. The scale is going to register no weight, and you can see it mathematically also by actually doing the you know, you'll get W equal to 0 because mg is the only force acting on it, and mg should be equal to ma, and so W is 0. You see that? So yeah, so this is just a way of trying to understand what goes on about you know, the why there's such a thing as apparent weight, and why the astronauts falling down, they're kind of falling around the Earth in free fall, and so they're you know, an object there would not show any weight, and that's the reason. Just thought that it might make more sense if you saw it this way. And so when you come across a problem like this, you may apply these principles to solve that. So there's actually just one more topic, so I think I'll finish that, and then we can take some time to talk about, you know, the entire chapter and try to solve problems. So I'm going to move on to, I can just pause to see if anyone has a question. You can go ahead and ask if you have a question right now. Okay, so going to move on. So the last topic is called Kepler's laws, and sometimes it's an optional section of the chapter, and but it's kind of interesting and it's very useful, so I typically do it, but I don't spend all that much time on it. But I think you'll it's not difficult, it's just you know, a lot of computation sometimes. So Okay, so Kepler actually put forth 3 laws of planetary motion sometime around the time of Newton. No, actually much earlier. It says 1570. Well, okay, about a century before Newton. And he obviously those days there were no telescopes and nothing that could have helped him much. But he kind of observed with some kind of homemade telescope. He observed the um, motion of the planets uh, around the Earth, and he kept careful track of it. Um, it's probably not very easy, but um, he did that, and he came up with 3 laws in the sense that they could not have been verified at the time, but he just put forth from his observations the following laws. And okay, so his first law was that all planets are actually moving in elliptical orbits about the sun, with the sun at one focus, and that may be difficult to understand if you're not very clear about what an ellipse is. So, for example, a circle has one center, right? But an ellipse, being elongated, does not have a center. It has 2 foci, as they are called. It has 2 focal points, and that's how we define an ellipse. So, according to Kepler, the sun occupied one of the 2 focal points, and the other, there was nothing there. So, according to him, every planet has an elliptical orbit about the sun. It's not circular. And so, for the ellipse, the shorter axis is called the minor axis, and the longer axis is called the major axis. So, that's something that might be interesting. So, yeah, so this is just some review of an ellipse. Again, you don't have to know most of it, because eventually you're just going to use, the third law is the only law that we really use. But this is just for your information, that you see the 2 focal points, F1 and F2. So every ellipse has 2 focal points. And we really talk about the focal points rather than any center of the ellipse. And so the major axis is, the long axis is called the major axis, and half of it is A. So it's called the semi-major axis, and B is the semi-minor axis. As you can see, it's one half of the minor axis. And we define the eccentricity of an ellipse as how elongated it is. And it's given exactly by that ratio C over A, where C is the distance from the ellipse to, from the focal point to the axis, you can see. And again, this, you will not be tested on this, but I thought to understand Kepler's laws, it may be useful to just have an image of an ellipse in front of you and see what is meant by a focus, right? And okay, so basically, this is the first law, that the sun occupies, for any planet in the solar system, and probably any planet around any other star, you can have, you have this planet that um, the sun occupies one focal point of the orbit that the planet assumes around the sun. The orbit is an ellipse, and the sun is at one focus. There's nothing on the other focus. And so these are a few examples of orbits. So the orbit of Mercury, see the orbit of Mercury, right? It's has the largest eccentricity of the planets. So it just means it's an elongated planet. It used to be Pluto, but I don't know, some of you may be aware of it, that as of 2006, Pluto was removed as a planet. It no longer is a planet. And if you look at Halley's Comet, you can see that it's got a very, very high eccentricity of 0.97. I guess, okay. I may just neaten up this before I post it. So the small dot that you see is the sun. So it's a very, very high eccentricity. I guess Mercury should be the lowest eccentricity. That seems to be wrong. They're the largest. Okay, so the Halley's Comet has the largest eccentricity, as you can see, right? It's got a very, very eccentric orbit. It almost scrapes the sun on one end and has a very, very far off. It goes off very far on the other end, and so on. So we are going to focus only on Kepler's third law, which I mean, the first law is simple, that it just states that all planets have a elliptical path around the sun, and the sun is at one focus. But Kepler's second law we ignore because it's highly mathematical and we don't really use it as such. But going on to Kepler's third law, and that is the end of the slide also. So for Kepler's third law, okay, so we derive Kepler's third law from the basic satellite equation, which I think I've shown you at many points in the slide. So assuming that the orbit is circular, which is, we don't have to assume, but just to derive the expression. So you see the formula on top. So that's the gravitational force between the sun and the planet is gm sun m planet divided by r squared. And that should be equal to the centripetal force mv squared over r, right? We've seen this relation many times. So, and if you put v equal to 2 pi r over t, you get this. I mean, you can try substitution, you get this. That t squared is 4 pi squared over gm sun r cubed, and which is all that stuff there is called ks. So all it means is that now, since the 4 pi squared over gm sun is a constant, right? Because m sun doesn't change. So it just means that around a central object such as the sun, you have that the ratio of t squared over r cubed is constant, which means that if you take two planets, let's say you take the Earth and Neptune, you'll have t squared equal to this constant times r cubed for the Earth, and p squared equal to the same constant times r cubed for Neptune, right? So you can take a ratio. So t Earth squared divided by r Earth cubed equal to t Neptune squared divided by r Neptune cubed. Do you see what I'm saying? You can, so that's become a pretty important law, because if we can find out the time period of another planet, say Neptune, and compare it with Earth, and if we know Earth's distance from the sun, we can actually find out the distance of Neptune from the sun by using that ratio, because t squared over r cubed is the same for all planets. So if you know the t and r for Earth, you can know the distance of other planets. And this is exactly what Kepler did. He would find out the time periods of various planets by actually tracking them on a nightly basis. And by using his law, he figured out how far off they are from the sun. I don't know if that makes sense, but anyway, that's Kepler's third law, and that brings us to the end of this. So I'm going to go back to the screen here, and you have a chance to type in anything you want. Okay, I'm wondering if that made sense, and if overall you think you have a pretty good grasp of satellite motion, including how to find velocity, period, etc., and relation between little g and big G. And I know that the vector form of Newton's law, there are 2 questions on it that may need some work because that's adding and subtracting vectors. But yeah, I would love to hear any comment. I mean, are you feeling better about this material? We are done with chapter 6. Does anyone want to say anything?
I had a question. I couldn't find the homework 6 that you said you posted. Was that in the Blackboard that you made?
Yeah, I put it in section 041042. Did anyone see it?
I looked for it, but I couldn't find it either.
I don't see it in here right now.
I see.
There's only 5 things.
Oh, I see. So did you find my lab materials though? Did anyone find the lab material?
Yes.
Yeah, I'm wondering where it went then. I need to go check on it. So I'm assuming that somehow it didn't show up. Okay. Thanks for letting me know. So did you go to the Pearson Mastering Center? That's where it should show up, right?
For mastering physics,
Yeah.
last week I completed a homework 6, but that was for Dr. Colt that
Right,
Dr.
right.
assigned.
I
Right
don't
now,
think
though,
he
when
would grade yours because he
Yeah.
has, yeah.
And it's been graded, and it shows up in Blackboard as a grade. However, when I checked mastering physics just now, it
Yeah.
shows the same assignment again, but all the problems are it's like I have to redo the assignment even though it's a completed assignment.
Oh, so that could be my assignment. They're different numbers, right?
These ones look pretty much the same. It's the same amount of questions, it says.
Is it like
There's one that says section 041, chapter 6 homework, so I think that's what we're supposed to do.
Yeah, that's the one. Yeah.
And there's
Yeah, I see
9
that.
problems. There's 9.
Yeah, there's 9 problems exactly. Yeah.
Okay.
So now then you can see it. So there seems to be some kind of confusion. Yeah, so it means that most of you can access it now, am I right? Because I mean, if you want, you can look right now if you're on your screens and see if you can find it on Blackboard. Though I don't know if from Teams you can switch easily to Blackboard. Depends if you have it open with you. Yeah, so I don't know if I should post it again or do you think you see it?
Are you talking about for the homework assignment?
Right, right.
I see the homework assignment on mastering physics, but not on Blackboard.
Okay, yeah, okay.
That's the
I'm
only
sorry.
place it should be, isn't it?
Since I arranged the homework through mastering, it should appear on mastering. Yeah. So does that help? You know, for is that helpful for everyone to access it? Just wondering. So to get it, you have to go to mastering physics because I'm getting it graded through mastering. So yeah, I guess if one person can see it, so can the rest. Yeah, so please, I'm going to try to coordinate with Dr. Fulton to see if we can just make the same homework. You know, if not, it's confusing, right? But we'll see. It's need not be too confusing, I guess. Okay, so I guess since most of you did not see the homework because of not knowing where it is, you may not have questions on the homework as yet. There's all of next week your questions. But if anyone has a question right now, you can ask. They're sort of at the end of the hour, but you know, not a big deal if you have questions. And regarding office hours, so earlier I had all these hours free that your sections are in, or your class hours are in, and I had office hours on at least 2 of those. So that's wiped out now. So finding office hours may be hard, but I was just thinking that, every time we meet for a synchronized lecture, we can have an office hour right after. And if that doesn't work, then you can, um, chat on Teams and find a time that would work, or just email me and set up a time and we can meet on Teams where we can, discuss using a whiteboard and, actually like, like as if we are in class, we can discuss all your questions. I think that would work, right? So did anyone have another question? Okay, so please try the problems, and I guess I should make an assignment for the lab, right? So I'll make it into an assignment on Blackboard. It will be under section 041042, and you can turn it in right at that link. I think you're used to that. So turn in the homework and the lab. I think 1 week is enough for both. And if you don't think it's enough, you can let me know. Because I know people have different internet, capabilities, and so I'm not going to penalize anyone because their internet connection is not very good or they don't have it on a regular basis. So, but you have to reach out and let me know that you're having this problem, and we can take it from there. Is there I guess I have nothing more to say. I was wondering if anyone had any other questions right now on either the lecture or homework or lab or whatever. Okay, if there's no question, I just wanted to mention that even if I don't invite you, would you be able to get into the synchronized classes? I think all you have to do is go to the calendar, right? And go to the time slot and click on that, and it should take you to the meeting. Because for Monday, I think Dr. Wright has made this block which says midterm exam 1, and I'm unable to get rid of it. So, because I need to make that slot into a invitation team, but I'll see if I can get around it. So if you don't get my invitation for Monday, it just means you can, I think you can click on that, join the class.
Yeah, I think if anything, we can just click on the team and join the call as it's happening too.
So yeah. I think that would work. Yeah. Yeah, that sounds good. And yeah, you can keep trying the homework, and anytime you want, I can answer questions on the homework. Just try, if you can catch me on Teams, that would be awesome. Just check if I'm available, because there's a whiteboard that we could use and actually draw diagrams and equations, so that would be really helpful if you had questions. Okay, so I think I have nothing more for now, and we are at the end of the time period anyway. Yeah, so those who have no questions